Okay, friends, so before we get any further into this negative numbers topic, I think it's going to help us to look back a little bit about a little bit of number history and also the way to represent numbers visually, because I think it's really going to help us understand where negative numbers come and go from. So if you look back thousands and thousands of years, kind of to the dawn of mathematics, the most basic kind of stuff that was happening was counting. And you've probably experienced this if you've ever seen a small child getting excited about counting something. Like I remember when our son was really little, counting steps, or counting tiles, or counting stairs, or counting rocks, or whatever. It was 1, 2, 3, and then, count higher and higher and higher and higher. They were counting with what are called whole numbers. 1, 2, 3. So you start with 1, and then you go in increments that are equal up as high as you want to go. So I think when folks got really clever, they decided to represent that kind of one-dimensionally, not zero-dimensionally, like a letter or a number, but one-dimensionally by having 1 be here, having 2 be out here, a certain distance. And then you can have 3 be the same distance from 2 that 2 is from 1. Which also tells you that 3 is twice as far away from 1 as 2 is. That's super clever. You can go as far as you want. You can go up 4, or 5, or 6, or 7, or 8, as far as you want. And that was great for probably thousands of years. But then if you go back and look at the history of when big things change, there's a group called the Pythagoreans. You've probably heard of them because you've heard of something called the Pythagorean theorem. And if you haven't, you're going to learn it in this class. But even before the Pythagoreans had the Pythagorean theorem, the Chinese had it a century or a millennia earlier than that. But that's not important. What's important is some of the stuff that they came up with their Pythagorean theorem. And some of this stuff is actually used by carpenters today. For example, there are special triangles called Pythagorean triples that carpenters will often use to check square of buildings. For example, a 3, 4, 5 triangle, or a 6, 8, 10 triangle, or a 5, 12, 13 triangle. These are special triangles because they satisfy the Pythagorean theorem, and all the numbers on the sides of those triangles are whole numbers: 5, 12, 13, 6, 8, 10, 3, 4, 5. And all of a sudden, the Pythagoreans began to ask, what happens if you have a triangle that looks kind of like this? So it's got a 1 and a 1. What would this have to measure here? And that created a rift in the Pythagorean culture because they did not have an idea of what that number would have to be. That number is not a whole number. 1 won't work, 2 won't work. It's got to be something between 1 and 2. And that's where it forced humanity to start dealing with the space between the 1 and the 2. As it turns out, that question mark is somewhere right about here. And we'll study that more in this class too, when we start taking square roots of things. But questions like this forced humanity to deal with the space between these numbers. So it wasn't that it was just discrete points, bop, 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 bop. It was a continuum. And we very often put like an arrow going outward forever to indicate that there is no stopping. You can keep adding and adding and adding. And then it wasn't very long until people began to realize, wait a minute, I mean, 1 makes sense for things like 1 table or 1 shirt. But how about like $1 or 1 other unit of whatever you want to measure? You can have smaller pieces of that. And then they began to realize that you can creep backwards from 1. And that is where the history of 0 really kind of comes in. This idea that there has to be something here that is the same distance from 1 that 1 is from 2. And once we had 0, and I say we, meaning the global community of mathematicians, it naturally led to what is below 0. I mean, should it stop there? Now, for certain contexts, yes, it should. Like, you can't have negative feet, but you can't have negative dollars. You can be indebted to someone. So you can actually go to the left of 0. And that's where we started chatting about negative numbers. So you can go -1, -2, negative as far as you want. But the idea is the ruler is consistent. These spaces are all the same, and you can live in between the spaces. Now, what's interesting about this is, and this of course goes forever as far as you need it to go too. What I find super interesting about this line is, I don't think we're done with it yet. I mean, we're done with it for what we need to talk about in our culture right now as it sits. But when I look at the number line, and I forget the guy's name who invented it. I looked it up when I was prepping this video, and I've since forgotten it. But I happen to notice this is a one-dimensional thing. Left and right, that's one dimension, length. What happens if we go up and down from it? What do you get then? I think that's where things called complex numbers could be represented. I've never seen it represented that way, but that could be the next step. And what if we were to come forward and backwards? Enough of that. We've got enough on the board right now, I think, to take us into the next little bit of our notes. So let's do it.